Hello, today we're going to be talking about work and machines, and this can be found in chapter 4 in the first section. So first off, let's talk about work. How would you define work? Well, the definition of work is force applied through a distance. So here's a question. If you push against the desk and it doesn't move, have you done any work? So I'm applying a force, but it's not moving. So have I done any work? Well, let's look at our work equation. Our work equation is this: work equals force times distance. So if our distance is 0, 0 times any amount of force equals 0. So therefore, according to this equation, if we put force on an object, but the object doesn't move, we haven't done work. Work is in joules, which is a newtons times meter. So a newton meter is 1 joule. And remember, newton is a kilogram meter per second squared. We learned that with force. Okay. So again, force is measured in newtons. Work is measured in joules, and it's named after the guy that kind of came up with all this stuff. So force and our direction of work. So we've already learned that if you don't have any distance, there's no work done. But now we're going to talk about the direction of the work on the force. So force that is parallel to motion. That means force is applied directly to an object in a straight line. So we're not pushing off at any angles. It's straight on push parallel motion. When we do this, there are no angles that modify the amount of force directed on an object. So the amount of force that we put in is directly applied to the object. If we have force perpendicular to motion, so if I have a force this way and I'm pushing this way, but motion is going to go this way and I'm pushing off that, so force applied at a right angle to the motion, there's no work done because there's no distance moved in the direction of force. So my object is moving this way and I'm pushing off to the side, like say you're pushing a car out and there's somebody in the front trying to push on the front wheel to try to get it to go in a different direction, but there's no force and there's no motion in that direction. That means I haven't done any work because, again, if there's no distance, force applied through distance, there's no work. So again, example would be like pushing on a side of a car that's rolling straight ahead. You're pushing on it, but you're not actually getting any work done because you haven't applied a force through a distance. So let's talk about force at other angles. Work is less due to force directed at a different direction than motion. The most common example that I can give is like, say you're doing a lawnmower, and the lawnmower is down on the ground and the handle is way up in the air, and you're pushing up at the top. Now, some lawnmowers that have like a nice steep angle, so you can push really easily. Other ones, like they're really jacked up, so you're trying to push front, and as you're pushing, the back tires of the mower keep coming off the ground. And this is because of all the different angles that are involved in your force. And when you do this, you're actually reducing the amount of work that you do because of the angle. So the shallower the angle, the more force is applied, which leads to more work being done. And remember, work is only done when you're applying force to an object and it's moving, okay? So let's hear a question for you. So where is the work done on a bullet fired from a rifle? So if we think about that, we have a shell with the bullet in it into the chamber. It's fired, and then the bullet is pushed. The force is done with the push as it's being pushed. But as soon as it exits the barrel of the rifle, there's no more force pushing behind it because the exhaust, the gases and stuff are expelled and it dissipates once the barrel is gone. So work is done on a bullet inside of the chamber and the rifling, which makes sense that a rifle has much more velocity, more force because it has a much longer barrel, which means much more work can be done over that distance versus like say a pistol, which has a very short barrel. And so there's not a lot of work can be done there, so you have much less velocity, much less force coming up. Here's another question. Where is the work done when you throw a baseball? Obviously by now you're trying to figure out, well, it's from as long as I'm holding onto the ball and that whole range of motion as I go to throw, that's where work's being done, and you would be right. So let's now talk about machines. Machines are what we do because work is hard. How do we make it easier? Well, it's not an option. You can't just get out of it by saying, oh, somebody else can do it. Work has to be done. So what do? Well, we use machines, and machines are devices that change the force that we're working or increase the motion from work. So machines basically increase our force and speed. They change up the energy that we're putting into it and doing different things with those. And there are 5 types of machines. We're going to talk about the simple machines first. And these basically does work with only one movement. It only has a simple machine has one movement. All right. And like I said, there are 6 types of them. You want to know these. These are very, very important. You'll be tested on them, quizzed on them, all that kind of stuff. So make sure you know these 6 types of machines. So we're going to go through those. So here are the 6 simple machines. The first one we're going to talk about is a lever. Now there are 3 different kinds of levers. There's a first class, a second class, and a third class. These are all in relation to where the fulcrum is in relation to the input and output force. Think of the input force as the force that you apply. The output force is the work that gets done. You can see like a pair of pliers, a wheelbarrow, or like even your biceps. And each one of these have a different, and we'll get into the different types of levers and stuff later on, but each one of these has different advantages for using them. The second simple machine we'll talk about is a pulley. Now, pulleys are really interesting because they use a change in motion, a change in direction of motion. And then you can see as we move on down this line, one pulley from the ceiling, we're pulling 100 newtons. 100 newtons is on this rope. We're moving 100 newtons 10 centimeters. And the rope moves 10 centimeters. But if we start adding more pulleys in there, we're trading the distance we pull for the amount of work, the force that we can lift up with. So you notice here, when you finally get down here to 4 different pulleys at a block and tackle, we're only pulling 25 newtons, but that is multiplied by 4, which means we're moving up 100 newtons. The trade-off is we're pulling that 100 newton force up off the ground 10 centimeters, but we have to pull our rope 40 centimeters. So again, we're trading distance, all right, for work that we're doing. And there's always a trade-off that we have with using a machine. Remember, machines convert work or force and distance, okay? Third type of machine is the wheel and axle. Now, wheel and axle, you'll notice here, well, that's not much of a wheel there. Well, in actuality, a crank on the end of a rod right here like this is actually your wheel, because if you notice, this wheel is a large circular pattern. And in the center, we have the axle. And like, say, raising a well, right, it's very easy to crank because this lever reduces the amount, not lever, but this wheel, in essence, moves the cylinder around, the axle around, and that makes a distance. And also, think of it the opposite way. It takes much less force to rotate an axle, and the larger wheel you go, the faster you go, which is why 10-speed bicycles and stuff all use the wheel and axle. Okay, and that's how that works. The fourth machine we're talking about is an inclined plane. An inclined plane is basically a ramp. Is the simple version for it. And what that does is that rather than trying to lift vertical, we stretch it out over a long period of time. And so the force that it takes to go up is much reduced than if we were to like deadlift it at the very end. So it's a lot easier to roll up a ramp. And the longer your ramp, the easier it is to roll heavy objects up. The steeper the ramp, the harder it is. And that's because we're using force over distance. Remember that work is force over distance, and an inclined plane increases the distance where we're using that force. Screws is the fifth machine. Screw is actually a ramp, an inclined plane wrapped around a cylinder. So in essence, it's kind of funny because technically you could say, well, a screw is basically a wheel shaft, a wheel, an axle with a inclined plane wrapped around it. And technically that's correct. It took them a long time to try to figure that out, but by that, they'd already called it a simple machine for so long, they just kept it as a simple machine. But you'll notice basically that it's a ramp or an inclined plane wrapped around a shaft. And basically what that does is as you turn it, you're basically changing the distance, the force, and all that kind of stuff and using it. So a screw is a simple machine, though some argue it's not. And there is a validation to that, but it's in our list, so we leave it as it is. And finally, the wedge. The wedge is really interesting because it changes the direction of the force. A downward force on the wedge produces a perpendicular sideways force, which causes it to split, which is why it works really good for splitting wood. Also, door stops. We kick it underneath the door, and as the door tries to move, it changes the direction of the force from the door going, say, left to right, and it changes that swinging force to a down and increases the friction, which causes it to stop. So those are the simple machines. Let's talk about compound machines. What is a compound machine? A compound machine is a combination of two or more simple machines. So basically, you put a couple of simple machines together, and poof, you have a compound machine. For instance, a common machine that everybody uses is a scissors. Well, that's actually two different wedges, one wedge on each one of the arms, and two levers, basically the handles that you squeeze together. Bicycles. Bicycles are made up of pulleys, wheels, and axles. We're changing the direction of the chain as it goes around. And then we have wheels and axles of different sizes to change our speeds. Why do we use machines? Well, machines increase efficiency. Efficiency is the ratio of output work to input work. Basically, easily saying machines make stuff easier to do. We're changing how much work we have to put into it versus how much we get out of it. And we usually measure efficiency in percentages. And here is our equation. It's output work divided by input work times 100, and that gives us the percentage. So it's output work divided by input work times 100, and that gives us how efficient our machine is. And we can increase efficiency by reducing friction, lubrication. Efficiency, the only way you really can increase that once you have a machine set up is to reduce friction, because we know friction always takes motion and turns it into heat. All right, so we got to reduce friction as much as possible. No machine is 100% efficient because we have friction. Right? So the useful machines. So if machines aren't that efficient, in other words, it takes a lot of times more energy to put in. We put way more energy in than we get out. Why do we use them? And like I said before, we use them because it changes the way work is done. The force, we put a light amount of force in, we get a lot of force done. There's a trade-off here, and that's why we use machines. Machines change the way work is done. For instance, increasing speed. To increase speed, there's a decrease of force. Think about a bicycle. How hard is it to pedal uphill? Well, it's a lot harder. You have to push harder, right, to get uphill, especially if you can't change your gears. If you have a single speed bike, or if you have like a 10 or 20 speed bike that the gear shifter is broken on, you're stuck in one gear. And if you're increasing up the hill, it's a lot more force. You have to pedal a whole lot harder. But if you're on flat ground, that pedaling is very nice because you're changing the force for speed. Okay, but it costs force to do so, which is why cars have gears. Changing direction with force. We change direction. Think of a wedge splitting a wall, pushing it up a ramp. Changing the direction is a lot easier going up a ramp than trying to deadlift a whole lot of pounds. Okay. And the third reason we use machines is we increase force. So force increases, but the decrease of speed. Think about a car jack. You take lots of movement. You're moving your hand up and down a lot to get that little bit of movement up on the car to change the tire, but the car is really, really heavy, and there's no way you could lift it up by yourself. So we use a machine that takes the distance or the amount of work time that we put into it, and we trade that off for the lifting force. Mechanical advantage, and this is why we use machines, is basically it's a measurement of the effectiveness of the machine at increasing the force. All right, mechanical advantage, and here's the formula for that, which is the output force divided by input force, and that's just our mechanical advantage. That's in newtons. Like how advantageous. Notice the output force divided by the input force. So if we're having an output force of, say, 1,000 newtons to lift a car, but we're only putting in 100 newtons, right? So 1,000 divided by 100, that should leave us with 10. So that would be a mechanical advantage of 10. Okay?